Once more with feeling. I'm Ray Myers. Welcome to Craft vs. Cruft, and a quick follow-up on the last episode. That was an explanation of a compiler correctness proof. That compiler was concerning a toy language called IMP, and the original proof was by Alex Otian. At the time, I was experimenting with making kind of an on-demand proof explainer tool. So for that reason, there was synthesized speech. But, for the purposes of creating video content, I really always should be doing these in my own voice. So Federico, Nissan, I hear ya. I'm really pleased that there was some interest in this content, so let's go ahead and do it right, shall we? By the way, if you want to hear me talk more, there is also a new podcast called The Coding Agency. You can find wherever podcasts are sold or thecodingagency.org. If you're just here for the Anthropic Fable memes, we got you covered there too. So without further ado, this is aimed at people who are interested in how programming language semantics are used to prove results, including compiler correctness. All right. To see how this tiny verified compiler works, first let's meet the two languages it connects. The source language is IMP, a tiny imperative language with just 5 commands: a skip that does nothing, an assignment, sequencing, an if, and a while loop. The meaning of IMP is defined by its semantics. Running a program transforms memory, taking a starting state to a final state. That is the behavior the compiler must preserve. So what exactly is that meaning? There are some fancy terms here, but you can think of it like a formal reference interpreter, defined so that it can run one step of interpretation at a time. This definition is in a format called Big Step Operational Semantics. There are other formats. Now, this takes the form of a relation between a start state, a command, and an end state. A state, written sigma, is just the memory, a map from variables to values. The relation is made up of inference rules, one per kind of statement. Here's the rule for assignment, which we'll be coming back to. On paper, a semantic rule is written like a fraction. Above the bar, we have some expression that evaluates in state sigma to a number n. So running assign a to x will take sigma to a copy of that state with x bound to n now. In Lean, that relation is defined like a data type, and each rule is one of that data type's constructors. It takes a hypothesis in and a conclusion out. So for our program, 2 plus 3 is 5, and x ends up bound to 5. So now the compilation target, which is our stand-in for assembly language. It's a simple stack machine in the spirit of bytecode. For instance, JVM and WASM are also stack-based. There are no variables in its expression. It computes directly on the stack instead. So a statement in this language can push a literal, it can add, subtract, or multiply, each by popping 2 of the values and pushing the result. The load and store instructions move values between memory and the stack, and jumps handle control flow. Compiling means turning an IMP program into a list of these instructions in the stack language. So, what do we mean when we say a compiler is correct? There are a few ways to model that. This is a common one, called a commuting square. On the top edge is the language semantics. You run it, you get a result. Down the left edge, the compiler turns a program into our stack machine code. And along the bottom edge, the stack machine runs that code to its own result. We say that the square commutes when the two routes agree. Both the semantics and the compiled program end up with the same result in memory. Here is the square for the concrete program we were just looking at. It's assign 2 plus 3 to x. The semantic rules transform the starting memory into a memory where x is 5. The compiler produces this stack machine code, and running that creates the same memory state. The two routes agree. In fact, they agree for any valid program. That's what we must prove in order to prove the compiler. This proof is organized in a tree of lemmas, the final theorem, and a couple of supporting lemmas under it. By the way, lemmas are the same as theorems. They are results we prove. Calling the intermediate results lemmas is for clarity. It's just documentation. At the very bottom, there's one lemma per kind of expression. The name of the game here is structural induction. We're considering every kind of IMP expression, which is to say a number, a variable, or an operation on 2 smaller expressions. The recipe is always the same. Prove some property on the smallest shapes directly, then show for an operation that if its arguments hold, then so does the combination. This proves the property holds for all possible expressions. That's structural induction. The same recipe works for programs, building them up from their statements. Looking now at the top theorem, com.compileCorrect. It takes any program C, the states sigma and sigma prime. It also takes a proposition H that supplies a proof that the program runs sigma to sigma prime. Propositions are often called H, short for hypothesis. Conceptually, this theorem states that compiled code reproduces that program result. Formally, it says there exists a fuel budget, and we will explain fuel in a moment, but there exists a fuel budget such that executing the code returns the configuration with final memory, sigma prime, and the program counter moved to the end. Since the notation may be unfamiliar, I'm going to explain it at every turn here. Sigma is the memory state, mapping variables to values. Sigma prime is the state after running. A configuration written mu is 4 things: code, stack, memory, and program counter. The double arrow represents the semantics. Command C takes sigma to sigma prime. Execute runs a configuration capped at a number of fuel steps. That's what fuel is for. It's a cap on recursive depth. Lean functions must terminate, but a compiled program can just run forever. So the beginning of a theorem statement exists a fuel such that it means that there is some fuel that is enough, so this program halts at some point. Proceeding to the proof, execute lemma does some heavy lifting. It states that if we reach the final configuration, some fuel budget is enough for execute to return it. That turns our reachability path into a real fueled run. Applying that lemma splits our goal into 2 obligations. First, the machine can reach the end configuration, the one carrying the final memory. Second, that it takes our program counter to the end. There's nothing left to run. The first obligation is the lemma one level down, compile correct aux2. We'll go there next. The second, we can discharge directly. The program counter sits at the code's length, so there's nothing left to run. So, the top theorem is done, provided we can prove those lemmas. We'll go down next to com.compileCorrect aux2. This essentially strips away the fuel boilerplate so we can focus on the interesting results. It takes the same inputs as before, that same proposition H, that the program runs sigma to sigma prime. Conceptually, this means the machine can run the whole compiled program to completion. Formally, there is a reachability path from the start with memory sigma to the end with memory sigma prime. The end is when that program counter is at the code's length. One new symbol here, reachable. It's an inductive data type defined in the project. It's built from 2 constructors, a single state machine step, and the ability to chain steps end to end. So if we have the reachable object from one configuration to another, it means we've shown the machine can get there in some number of steps. The rest is the same as before. To begin proving this lemma, we inline the compile function into the proof state so we can analyze it. The code is the command's body followed by a single stop. The heavy lifting here is by the lemma compile correct aux, which we'll see next. It runs the body with nothing before it, an empty prefix, and just the stop after. The program counter is parked at stop, the memory is in its final state. One more step executes that stop, which simply moves the program counter to the code's length. This layer is done and we can get into the lemma where the real work is done. Alright, we're finally ready to look at a lemma that analyzes the IMP language's commands, com.compileCorrect aux. It adds 2 inputs, pre and suff, which are short for prefix and suffix, the code before and after the command. It keeps the same proposition H that the command runs sigma to sigma prime. Conceptually, the claim is that a single command does the right thing when it sits inside a larger program. Formally, we claim reachable can be constructed with these 2 configurations. One configuration is reachable from the other. The difference between the 2 configurations is that in the latter one, the memory has been updated from sigma to sigma prime, as usual. Also, the program counter has advanced to the end. In notation, the only new thing here is that we're wrapping the command's compiled code in a prefix and suffix. The double plus joining them is just a list append. There are arbitrary instructions before and after that, and compile offset compiles a command starting at some program counter. Reachable and the configuration tuple are the same as before. To prove this, we follow structural induction, the same recipe as before, now on programs. We split by how the program ran, one case for each kind of statement: skip, assignment, sequencing, if, and while. In each case, we show the machine reaches the right state, assuming the smaller commands already do. Take the assignment case. We assign some expression to x. First, we run the expression's code, and that step is a call to the leaf lemma axp.compileCorrectAux. It leaves the expression's value on the stack. Then one store step writes that value into memory, giving the updated state. This induction case is now closed, so we've arrived at the leaf our descent was leading to. This is our leaf, axp.compileCorrectAux. It's the compiler's correctness result for arithmetic expressions. That's what AXP stands for. Conceptually, this is saying that running an expression's compiled code leaves its value at the top of the stack. Formally, there exists a fuel such that executing the code returns the stack with the expression's value pushed on top and the program counter past the expression's code. In notation, a couple of new things for expressions. Eval gives an expression's value in a memory state, and the double colon pushes a value into the top of the stack. It's like a prepend operator. The configuration tuple and execute are still the same as for whole programs. A sub-expression's code isn't there alone. It's embedded in a larger program. So again, we allow arbitrary code before and after it and just require that the machine can reach the state before this expression's value has been pushed. Once again, we use structural induction on the shape of the expression. Lean splits the proof into one case per shape. Numbers and variables are the leaves, and the operators combine them. There's this tactic you'll see at every level, CerImp, called with the machine set. That set has the stack machine step function and its helpers. They do things like read the stack, update memory, and bump the program counter. So this allows Lean's CerImp tactics to do the simplifications that are very useful to us here. They essentially execute the state machine semantics in place on the goal in the proof state. So for instance, with a push command, the literal lands on the stack and the counter advances by 1. Whenever a single instruction has to run within the proof, this is the tactic that runs it. So, the leaves are easy. A number compiles to a single push. The counter advances by 1. This base case needs no more work to prove. Simplification closes that sub-goal. Now, an interesting case, a sum. This is where we can take advantage of the induction hypotheses, IH1 and IH2, each saying its operand's code already does the right thing. Recall that reachable just means the machine can get from one state to another. We string together two such journeys. The first, IH1, runs on the first operand's code, leaving its value on the stack. The second journey, IH2, runs the second operand's code. One final step executes add. It pops both operands and pushes their sum 5. The combined case will hold, given that the parts did. Induction ties it together. To be fair, the rabbit hole goes slightly deeper than that. We walked a simple case, a sum, but the trickiest case is the while loop. Here is how that compilation looks and why it's valid. First, we evaluate the conditional expression, leaving true or false on the stack. A conditional jump reads it. If true, we enter the body. If false, we jump past the loop. After the body, an unconditional jump goes back to the condition. The jump targets are just offsets set at compile time. This control flow mirrors the semantics. The two branches are the while true and while false rules. And because we know the source loop terminates by a hypothesis, the machine halts too. Some fuel always suffices. Here is what proving that one case actually takes. It's dozens of lines that mostly step the machine one instruction at a time and feed the induction hypotheses back in. Grinding through program counter arithmetic, you can spot the machine CerImp doing the per instruction work. We won't step through all this, but we do have one more payoff for you today. Beyond compiling correctly, we can also optimize. Here is the simplest optimization. constant folding. It finds sub-expressions with no variables and replaces them by their value. So the expression assign x to the result of 1 plus 100 times 2 becomes, at compile time, just assign to x the value 201. We get effectively the same program and same final memory, but the code is smaller. Here it goes from 7 instructions down to 3. So how does folding actually work? It walks an expression bottom up. A literal or a variable is left untouched. For instance, take an operation like a sum. It folds each side first. Then if both sides have collapsed to plain numerals, it computes that total in place and replaces the expression with it. Otherwise, it keeps the operation around the folded parts. On our example, 100 times 2 folds to 200, and then 1 plus 200 folds to 201. Minus and multiplication are the same idea, so that's the whole optimization, a few lines per operator. Is folding actually safe? It is, and here's the sketch, which is the same recipe as the compiler proof, structural induction. Start with the expressions. Folding never changes an expression's value. Conditions follow from expressions, then on to programs by induction on the command, and assignment leans on the expression case. An if or a while folds its test the same way. We get the same value, same states, folding is sound. So the optimizing compiler is also correct. We can simply reuse the compiler correctness theorem from earlier and compose it with this result about the optimization pass. That proof is just 3 lines. Apply the compiler correct theorem, rewrite with the folding soundness, and you're back to our hypothesis. The theorems compose. We would continue to do this as we add more and more optimization passes to our compiler. So finally, what does all this actually buy you? The guarantee is for every program and every input, the compiled code halts in exactly the final memory that the semantics said it should. Unlike testing, which would only show this for the examples we test on, this holds for all possible programs. Let's be clear about the assumptions this relies in, the so-called trusted components. The proof says the compiler matches our semantics. It can't tell you that the semantics are right, they are the specification. We also trust Lean Prover's kernel and that this idealized machine models the real target. Within those assumptions, a bug in this compiler simply cannot exist. This compiler and its semantics preservation proof follow Concrete Semantics Chapter 8 and the Stack Machine compiler from Software Foundations Volume 2. Development is in the repository. Thank you for watching, and with patience, the most tangled cord may be undone.